Hey, welcome. This is 3.5. We are talking about the derivative of trig functions. I love trig. This is one of my favorite sections. So be aware that there will be lots of trig problems on homework quizzes and exams. So pay attention to this section. It's a good one. I want to start. The question is, we're going to start with what's the derivative of sine x. Okay, again, I'm using this notation because it's an expression, it's not an equation that I've plugged in there. And we're going to figure out what this is. The way we're going to do it is using the definition of the derivative. So I'm going back to the difference quotient, okay? So the difference quotient says limit as h goes to 0, and I take the function and I plug in x plus h. Okay, then I subtract the function itself and I divide by h. Now those pesky little identities and sum and difference formulas that you thought you'd never use again, well, guess what? Here they are. So this right here is the sign of the sum of two things. And so we go to that formula sheet, and by the way, there are reference sheets in the back of your book and online. The Math Center has reference sheets with all these trig identities on them if you need them. So the sum formula for sine says it's sine of the first angle, cosine of the second angle, plus cosine of the first angle, sine of the second angle. Okay, that's the sum formula. Then I've got my minus sine x all over h, okay? And, usually what happens with proofs of things, this is a little proof for you, is there's some stage along the way that does some kind of tricky thing. And so it's not something that I would necessarily think that you would see initially, but once you see it, you kind of stack up all these little tricks in your bag, and sometimes you can, it just makes you better at seeing stuff like this, because as you go on in math, there will be more proofs and things. So what we're going to do with this is just reorganize the top and break this into two fractions. So I'm going to pull the sine x over here, so I'm taking this guy over there order-wise, and then I'm leaving the cosine x sine h over here, and I'm putting them in separate fractions both over h, okay, with the addition in the middle, which is legal. You remember, if there's one thing on the bottom, you can split it up into parts. Well, you can also group things and split it up into as many parts as you want. So that's the first section, the first little kind of trick. And then what we're going to do with this first fraction is we're going to factor out a sine x. So if the sine x is factored out, that leaves me a cosine h minus 1 over h. Okay, and in the second fraction, I'm going to factor out a cosine x. The reason is, I don't know if you remember that I wrote this in the limits section a little while ago and said these are limits that you should memorize. We had this one, and we had this one. I told you these are good to memorize. So a lot of times, the reason they're good to memorize is if you can create those in your limits, then that gives you some automatic numbers you can plug in. Look at what I'm looking at right here and right here. Those are those two limits. So I can actually take the limit of those, and this sine x doesn't have an h in it. So the h doesn't get plugged in here at all because it's in terms of x. So this just stays as sine x when I take the limit. And when I take the limit of this, I'm using my identity, I get 0. And the same thing happens with this term. The cosine x stays because there's no h in it. And the limit of this guy is 1. So the 0 wipes this sine out, and the 1 just leaves, and I'm left with cosine x. Okay, so that's a quick little proof of what the derivative of sine is. Now, the proofs for the other trig functions are similar. I'm not going to walk through them all. I just wanted to show you one, kind of start to get you used to what proofs look like. And but what I'm going to do is list them all out for you now. Okay, so the derivative of sine x is cosine x. That's the one we just saw. Okay, if you do this same process for cosine x, you'll actually get a negative sine x. If you take the derivative of tangent, you'll get secant squared. And if you do cotangent, it will do negative cosecant squared. Now, those are in your book in this section. Again, there's sheets in the Math Center with all of these derivatives for all the trig functions on them. You can look them up. I do not expect you to memorize them. I would like you to know these. These are two that come up often enough that they're worth putting in your brain. But the other ones, most of us always look them up. All right. Oh, I've got two. Sorry, I didn't finish my list. There's two more. The derivative, these are not memorizers. These are, write them down, look them up when you need them. Derivative of secant is secant tangent, and the derivative of cosecant is negative cosecant cotangent. Okay? All right, so let's do some problems with these. The problems are going to look the same, like regular derivatives, product rule, quotient rule. So we're still just practicing those things, but now in the context of trig. All right, so sine x, tangent x is our first example. So since this is a y equals, my notation is going to be dy dx is... Yeah, I look at this, I say, okay, I've got a product. I've got two things multiplied. So I am doing the product rule. And the first thing I'm going to do is write out the rule in context of my problem. So it's going to be the derivative of the first thing times the second thing, okay, plus the derivative of the second thing times the first thing. That helps me make sure that I have actually written down the product rule correctly, and now I can focus on the little pieces. Okay, this piece derivative and this piece derivative. So the derivative of the sine, I go up to my chart right here. The derivative of the sine is cosine. So now this is cosine times the tangent. And the derivative of tangent, I go up here, is secant squared. Okay. And then at this point, I would like you to reduce. And these are going to be like the problems that you did in pre-calc, where you just simplify an expression. So your game plan is you can factor things, you can rewrite things in terms of sine and cosine, you can add fractions. You know, we had a few tricks like that that help you reduce. And the most powerful one is right in terms of sine and cosine. That's the one that often works. So instead of tangent, I'm going to write that as sine over cosine. Okay? And secant is 1 over cosine and sine. Okay? So, and now if nothing cancels, then go back to what it was. You're probably done. But in this case, I can see that I've got a cosine upstairs and downstairs. Those cancel. Nothing's happening over here, so I'm probably going to just throw that back into secant squared sine x. That's cleaner than 1 over cosine, so this is going to be sine x plus secant squared sine x. Now you can see that each of these have a sine x. If you'd like to factor one out, sorry, my pen glitched. I don't know what that is. This is a plus. Okay, if you'd like to factor that out, that's fine. My rule of thumb is I only factor if it's going to cancel with something. So since I don't have a denominator, this is not going to benefit me greatly, okay? Although you look at this, and some of you guys might identify that this is the Pythagorean identity. You could replace that. That would make that really nice. So let's take a look at that. So there's some give in this, and it's a gray area as to how far to go, but we'll try to talk about that as we go along. This is the Pythagorean identity, okay? Sine squared plus cosine squared equals 1. And if you want to make a secant squared, I divide this whole equation by cosine. So that gives me tangent squared plus 1 equals secant squared. And I'm looking at this, and if I subtract the 1 over, I see that this is secant squared minus 1 is actually the Pythagorean identity, and I have plus. So this doesn't apply here, but that was worth checking, okay? So this is probably it. Right here is my answer. You could end here or here. All right, so that's one example. If you want to pause the video and try one, you would do example 3.39 in your book. That would be a good idea to try that, and then we'll go on to the next example. All right, welcome back. Don't be afraid. You see a unit circle down there. Everything's going to be okay. It will all come back to you. There's so much of pre-calculus that we use in this class. Bring it all back. All right. Finding the derivative. I'm going to say dy dx because I have, it's in terms of y, not f of x. So to write f prime of x would be incorrect notation. And I'm going to take the derivative. Now this is a quotient rule. Okay, I've got two things divided, so this is a quotient rule. So the first thing I'm going to do is write this out as a quotient. All right, low d high minus high d low. Square the denominator, and away we go. All right. Now I'm going to focus on these two pieces and actually take the derivative. So I've got x, and the derivative of secant, if I go up to my list, is right here. It's secant tangent. So this is going to be secant tangent. And here I've got secant x, and the derivative of x is just the coefficient in front, which is 1. So that doesn't do anything, it goes away. And I divide by x squared, right? And up top, I see that both terms have a secant in them. I could factor that out. But there's nothing really to cancel. So I'm done. Please do not, I know that you're very tempted, do not cancel these. Okay, if you are going to factor, or if you're going to cancel, you have to cancel an entire factor. So you would have to cancel this whole thing. You cannot cancel over addition and subtraction. So this is actually done, and there's no other simplification to be done. All right, that if you want to try one of these with a quotient, well, I had one for you, and I can't see it. Here it is. Example 3.40 in your book will give you practice with a quotient. All right, let's do another one here. We're going to use this unit circle. And I want you to find the equation of the tangent line to the function f of x equals 5 cotangent x at the point x equals pi over 4. Okay. Please no decimals in this class unless you absolutely must, like unless there's no way to do it without a decimal. So when I give you an angle pi over 4, I am expecting that that rings bells to the unit circle, and you are going to give me exact answers. All right, so the first thing, if we want the equation of the tangent line, the first thing we have to do is take the derivative of the function. Okay, the 5 just comes along for the ride. It's a constant out front. And the derivative of cotangent, I'm going to go back up to my list. Cotangent is negative cosecant squared. So my function is negative 5 cosecant squared x. Okay. The next thing that I want to do is find the slope. So what that means is plug in your x. So my x value is pi over 4. All right, and now I need to evaluate this. So cosecant is related to the sine. It's the reciprocal of the sine. So what this means right here is I want you to go to the angle of pi over 4, and I want the reciprocal of the sine. The sine is the y coordinate. So I want the y coordinate flipped over. That's what this is asking for. And then I want it squared because it's cosecant. So I'm going to go up to pi over 4. That's right here. Okay. The sine is the y coordinate right here. And I'm going to flip it over. 2 over root 2. And then I'm going to square it. The squared's the top and the bottom. So this ends up being 4 over 2, better known as 2. So that is the value that I'm putting in right there. And my answer is negative 10. So that's my slope. Okay. And then the last step is to plug that in with a point. Okay. So we're going to plug it into, you can use this formula or you can use this formula. I do not care. Either one's great. I'm going to use this one just because it's maybe a little faster. So I need a coordinate and a slope. Well, I've got a slope, it's negative 10. And I've got an x coordinate, it's pi over 4. But I don't have a y coordinate. So the way that you find that is just like you would in an xy table. You'd take your x coordinate and you'd plug it into the function, and that's going to give you a y coordinate. So let's do that over here on the side. So I plug pi over 4 in, and now I want, this is going to be 5 times the cotangent. Now the cotangent is the x over the y at pi over 4. So it's those two divided. So let's take a look. At pi over 4, the x divided by the y, that's root 2 over 2 over root 2 over 2, which is 1. So the cotangent is 1, and so that means that my y coordinate is 5. And that is the equation of the tangent line. Okay. I think that is it for this section. If you would like to, you can try some problems, and I will see you next class.